Before we begin the official work of Chapter 3, I want to do this section, which I've titled 3.0. You won't find this section in the textbook, but I've discovered that students often have a great deal of difficulty parameterizing curves and other equations in three-dimensional space. So in this particular section, we simply work through a lot of examples of how you might parameterize a curve or an equation in three-dimensional space, as well as two-dimensional space. If you haven't studied parameterization before, you will want to go back to sections 1.1 and 1.2 out of the textbook, where it discusses parameterization and calculus with parameterization. Remember from those sections that a parameter is a sort of dummy variable that shows up in the middle and helps us to calculate the curve of a particular function, but does not actually appear in the plot or the graph of the curve. In other words, on many occasions, the parameter represents time. So in a two-dimensional curve, we could have x as a function of t and y as a function of t, where x is the horizontal position of an object at a particular point in time, and y is the vertical position at a particular point in time. So when you plot the graph, you plot it on an xy plane, so t doesn't show up. But the parameter t tells you at what time the object is at that location. We can extend this into three dimensions, x, y, and z, where again, the x, y, and z give either the direction or the location of the object with respect to the x-axis, the y-axis, or the z-axis at a particular point in time. Let's go ahead and I'll share my screen with you and we'll get started talking about how to parameterize various curves in two-dimensional and three-dimensional space. One thing that you will want to remember from parameterization in Calculus 2 is that parameterizations are not unique. There are infinitely many ways to parameterize any equation or curve. So they're not going to be a one equation where you can check your work and be absolutely certain that you have exactly the right parameterization. Infinitely many of them will graph the same curve. And we'll do an example of this where we use two different parameterizations to produce exactly the same curve in three-dimensional space. The first thing you have to do when you're trying to parameterize a curve or an equation is choose which variable you want to be the parameter, or if perhaps you want a multiple of one of the variables to be a parameter. So on some occasions, it makes sense to use either x or y in two-dimensional space as the parameter, or x, y, or z in three-dimensional space to be the parameter. In many occasions, we let x or z be the parameter. It's a little less common to let y be the parameter, but that's just convention. That's just our habit. There's no logical reason for that. Let's take a look at this equation right here, which you'll realize is a quadratic equation because it has x squared and y squared as the highest degree terms, and the other terms, of course, are polynomial in nature. We want to parameterize this function of two variables, x and y. So g of xy is actually the variable z. So we have z equal to negative x squared minus y squared plus 2x plus 4y minus 1. And we want to parameterize it when the y value is 3 by setting the variable x as the parameter t. When we say we want to set the variable x as the parameter t, we mean we want to represent the other variables in terms of the parameter. So I want to be able to write y equals something in terms of x and z equals something in terms of x. In this particular example, we're told that the y value is going to be 3, which means that's a constant. So it is already set and isn't necessarily in terms of the parameter x. Once we know that, however, we can replace all of the y's with the value of 3, which would give us a plus 12 minus 1, which would result, of course, in 11. Then we could replace the negative y squared with a negative times 3 squared. 3 squared is 9 times the negative 1, gives us negative 9. So the negative 9 plus 11 will give us a plus 2. Don't forget that when you have a negative variable squared, that you have to square the variable first, then multiply by the negative. Once we have that, we can replace the variable x with the letter t as the parameter. And now we have z, which is the function g, written in terms of the parameter. And the equation becomes negative t squared plus 2t plus 2. We can write this as a parameterization where x is t, y is 3, and z is equal to that equation. When we plot this in CalcPlot 3D, we plot it as a space curve, r of t. For a different y value, we would obtain a different parameterization and a different curve. You would click in the select box, choose space curve r of t, and it would open up a menu with preset equations. Delete the equations and enter x of t equal to t, since we set x to be the parameter, y of t equal to 3, and z of t equal to negative t squared plus 2t plus 2. There were no restrictions on our parameter in this case, either from the equation itself or given to us. So we can allow t to vary as much as we want. The default is typically from negative 10 to 10, which is usually enough to see most of the curve. In this particular case, you can see the graph of it right here, and you can tell that what we have is a parabola, which is showing up in the plane where y equals 3. Since y is always 3, then that is the plane. Let's take a look at it now over here. Or actually, I guess I did not plot it. Okay, so we will stick with that. If you want to plot, oh, I did plot it. Okay, here it is. So you can see it right now. If we turn it sideways, you can see that y is equal to 3. I think I said 2 earlier, but I meant 3. You can see that it's right there in that plane where y is always 3, parallel to the xz plane. And it is, in fact, a parabola. Now, if you want to trace it, you can click on the trace button. And you can move the slider bar and we'll come at negative 10. And then you can see the position vector, which is in blue, and the black is a tangent vector and green is acceleration. And you can see that it is graphing as t goes from negative 10 to 10 in this motion right here. So it not only tells us where in three-dimensional space it is, but at what value of t it gets there. So if t represents time, then we know at what point in time it's in that position. If it's not clear how to parameterize an equation, then this is a good way to parameterize it. Set one of the variables, typically one of the independent variables, here either x or y, to be the parameter. And that's a good way to proceed. Let's now look at the next example where we find a vector parameterization r of t of the curve x equals negative 2z squared, which is going to be in the xz plane. All right, so we're going to use t as the parameter. Now it specifies that it wants the parameterization in the xz plane. The xz plane is the one that is coming out of the board towards you. So it's coming out this way at the value right there where y equals 0. And in fact, that would be the equation of the xz plane, y equal to 0. Everywhere on the xz plane, the y coordinate is 0. So in order to get the curve to be there, we have to set y equal to 0. Now, there are a couple of ways that we can proceed. We could let x be the parameter, which would make sense. It's already solved for x, and that would make it relatively easy. Or we could let the parameter be z. So we could do it either way. In this case, in the first one, I let z be the parameter since it's already solved for x. And if I make z the parameter, then I don't have to solve for anything. I just get negative 2t squared. This means that t in the third position of the vector of the space curve is t, the y is 0, and the x is given in terms of t, negative 2t squared. And then I could go to Calc Plot 3D, and I could plot this as a space curve. I could also have chosen x to be t, in which case I need to solve z in terms of x or t. If I do that, that requires me to isolate x divided by negative 2, then take the square root. Because the square root is not present originally, I get plus or minus the square root of quantity x divided by negative 2. And then I can replace the x, of course, with t. This gives me a different but equally valid parameterization, t for x, 0 for y, and plus or minus the radical for the z. Both of these parameterizations, are going to plot exactly the same curve. Let's take a look now at this one in 3D. So when we're looking at it, we've got this shape right here, and it's kind of hard to tell at first. It looks, well, it almost looks like a circle, all right? So if we're looking at this, though, we know that this lies within the XZ plane. And if you can get it sideways, you can see that. If we want to see the XZ plane directly, remember that you hold down the Alt key and press the Y key while you are clicked inside the main graphing area. And then it shows up that it's actually something rather different than kind of what we were expecting. We see this shape right here, and you can zoom out to see if it changes it at all, and it does not. And you can see that this actually sort of meets with our expectations based on the equation x equal negative 2z squared. I would expect a parabola. And because z is the dependent variable and x is the independent, I would have expected it to be opening to the left, which it is. Let's now take a look at a second one. Some common parameterizations. I split this into two different tables. They're both common parameterizations. The first table refers basically to elliptical or circular curves in two-dimensional, three-dimensional space. So when you're looking at curves such as ellipses or circles, what you have right here is the formula for an ellipse in standard form, x squared over a squared plus y squared divided by b squared equal to the number 1. Remember that a circle is really just a special case of an ellipse where a squared is equal to b squared. In other words, it's r squared, the radius squared. If we want to travel in a counterclockwise direction, which is the normal direction, then our parameterization is x equals a cosine of t, where a is directly underneath the x variable, y equals b sine of t, where b squared is directly under the y squared variable, and we let t vary from 0 to 2 pi. This will graph out the entire ellipse, but it will do it in a counterclockwise direction. What if we want to go clockwise, if we want to go this way? We allow x to still be a cosine of t, but we write y as negative b sine of t, and then it will trace it in the opposite direction. So we're not only producing a curve in space, but we're producing what's called an orientation for it or a direction for it. So it's being traced in a particular direction. And then you have the same thing, of course, for circles, where a and b are both equal to the radius. Let's now look at some other common parameterizations. In the first line, we have a line segment, which we've already done this one before. This is how to parameterize the line segment moving from the point x naught, y naught, z naught to the point x1, y1, z1. So if you wanted to go in the reverse direction, you would need to reverse the ordered pairs, the components. So this goes from the first point to the second point. And the parameterization is 1 minus t times the initial position vector of the initial point. So this is a position vector as opposed to a point. with round parentheses, it's a point, but with angled brackets, it's a vector. So this is the standard position vector from the origin out to that point, plus t times the position vector of the second point. So again, basically what this is doing is running back and forth between the 2 points, and t is restricted between 0 and 1. If you multiply them out, you can write them in parametric form, which is what we did earlier, and you would have this form right here. Now, the last two are basically what you do when you cannot think of another good way to parameterize your function. If you have a curve, y is a function of x, then you can choose x to be the parameter t, and then y becomes a function of t. But you can also let y instead be the parameter t, and then x becomes a function of y. So it will go both ways. And we can expand these ideas as well into three-dimensional space. Let's look at example 3, where we want to find a vector parameterization, R of t, of the ellipse that's centered at the origin. So the center of the ellipse is at the origin, and the ellipse is in the xy plane. That means that z equals 0. It's our floor, right? So the z coordinate is always 0 in the xy plane. That has a major diameter of 6 parallel to the x-axis. That doesn't mean it goes 6 this way and 6 that way if this was the x. That means it goes 3 in the x and 3 in the x, right? And again, it would be actually graphed in the floor, and this is the positive x direction, and behind the screen is the negative x direction. Minor diameter of 4 parallel to the y-axis. Again, that means that we'll go 2 to the right along the positive y, 2 to the left along the negative y. And we want to trace it counterclockwise, which is the typical direction. We want to set our parameterization to start at a particular point. We want to start at the ordered triple 3, 0, 0, corresponding to t equals 0. So we're plotting it in the plane, but we're plotting it as if it's a three-dimensional curve. In this case, the equation of the ellipse in working form in the xy plane is x squared over 3 squared plus y squared over 2 squared equals 1. So we set the parameterization that x is 3 cosine t, y is 2 sine t, and z equals 0. Since we chose the y to be positive, it will trace it counterclockwise. Now we have to make sure that this is starting at the ordered triple 3, 0, 0. When t equals 0 and we substitute it into each of the parameterizations, we do get the ordered triple 3, 0, 0. Or you could check it, of course, in the xy plane and you'd get 3, 0. This tells us that we have the correct parameterization. Now, you could parameterize this in 2D or in 3D. If you parameterize it in 3D, then you need a component for each of the three, x, y, and z. So you would parameterize it as a vector, 3 cosine t, 2 sine t, and 0, where t goes from 0 to 2 pi. And we can take a look at that one now, which is this one right here. So you can see that it is, in fact, going to be right there in the XY plane. I'm trying to get it right on edge. There we go. You can see right on edge that it is at z equals 0. And if you want to see the XY plane, then hold the Alt key and press Z. Now, notice that this is an ellipse, and I don't have it zoomed out enough to tell. Let's go ahead and zoom out one so I get a little bit more. Now you can tell it goes between 3 and -3 along the x, and between -2 and 2 along the y, which is exactly what we were expecting. Now you can also look at this parameterization and do it as a two-dimensional parameterization out there in two-dimensional space. And if you want to do it in two-dimensional space, then you can do that by the following. It's the same thing, but what we've clicked on is this box down here that says restrict view to 2D, right? Now, you may wonder what these other trace vectors are that you're seeing. That's because the trace button is clicked on. The black is a tangent vector, and the green is an acceleration vector. Blue is the position vector coming to it, and I don't see the other one, all right, which we often have. And you could trace it like this. You can see them coming around, all right? So we have a tangent vector, we have an acceleration vector, and we have a position vector. The position vector is going from the origin here out to the point. That's what position vectors do. If you click the box for trace, it will disappear. How do you know that it's tracing in the right direction? Animate and notice that as t goes from 0 to 2 pi, it traces it in the counterclockwise direction starting at 3, 0. Then you can be sure it's tracing it in the correct direction. If you take off the restrict view to 2D, then you'll see it out there in three-dimensional space. It's essentially the same graph as what I had before, just with the 2D box clicked. Let's now look at the next parameterization, which is another circular shape. This one is a circle, so a special ellipse where both a and b are equal to the radius r. We want to find a vector parameterization for the arc of a circle. The radius is going to be 5, so a is 5, b is 5, a squared and b squared are both 25. From point 5, 0, so this would seem to say that this is in 2D, since it didn't say 5, 0, 0, to point Q, 0, negative 5. Okay, so from 5, 0 to 0, negative 5. So if I think about where that is on a graph, 5, 0 would be out here, and 0, negative 5 would be over here. So the question is, which arc do we want? You have to be told, and it does say traveling counterclockwise. If we went clockwise, then we would get a quarter of a circle in quadrant 4 only. But it wants us to go counterclockwise. So what it's looking for is the arc that comes all the way around like this. And we want to travel in that direction. If you want to do it in 3D, you would just add z equals 0 for 3 dimensions. All right, so this is the one we want. We want it to start on the positive x-axis at 5, 0, travel counterclockwise with a radius of 5, and stop on the negative y-axis at 0, negative 5. In this case, we again are going to parameterize x equals 5 cosine t. We're going counterclockwise, so we use y equal positive 5 sine t. But we need to stop before we go all the way around. Since 0 to 2 pi would take me all the way around, then you should expect I should stop 3/4 of the way, 0 to 3 pi over 2. And in fact, that does work. Let's take a look at this one out on CalcPlot 3D. And again, what we are plotting when you click select is space curve right here, the second choice down. When we get out here, you'll notice that I have this one on restrict view to 2D so that we can see and make sure it's tracing correctly. I have in the box that t is going from 0 to 3 pi divided by 2. The number of steps just smooths out the curve so it's not jagged. All right, so now we're going to animate. And we're going to see that it's going in the counterclockwise direction from the point we wanted and stopping on the negative y-axis. And again, if you want to see it in three-dimensional space, click off the box to restrict to 3D view, and you can see the same curve. Remember that the X is actually coming out of the screen towards you. Let's now take a look at example 5, which is another circle. We want to repeat example 4. We want to find a parameterization for the arc of a circle, still with radius 5, but this time we want to start at the origin, 0, 0, and we want to stop at the point 10, 0. Now, if I have a circle, and my circle has radius 5, and I start here, and I end up here, at 10, 0, I know the radius is 5. That's a distance of 10. That must mean that these are endpoints of the diameter of the circle, which must mean that the center of the circle is in between. So I must be going either this way at the top, like this with an arrow, well, or this way at the bottom, like this with an arrow. All right. So it could be either one. And now that I'm thinking about it, I didn't specify. So let's see what we can do. So if I'm doing this one right here on top, starting at 0, 0, I'm traveling in a counterclockwise direction from 0, 0 to 10 pi. Notice that the blue and the pink are not traveling in the same orientation. The pink is traveling counterclockwise. The blue is still actually counterclockwise. All right, so interestingly enough. So if I'm looking at this one, I know that I'm getting half the circle, and I know that's a terrible circle, but bear with me. They're both going to be starting. Let's suppose I want the one in quadrant 1, so the pink one, starting at the origin, stopping on the positive x-axis. This is going counterclockwise. Now, how can I shift the center from the origin over here to 5, 0? What I need to do is I need to basically move the x coordinate 5 to the right. Well, how do you normally move something 5 to the right? You add 5 to it. So my x coordinate, which would have been 5 cosine of t, because the radius is 5, becomes 5 plus 5 cosine of t. And because the pink one is going counterclockwise, then I would have negative 5 sine t, all right, instead of a positive. And then I want t to go, I have to restrict the range so I don't go all the way around. Now I need it to start at 0, 0. So I've got to pick my angle for the parameter. So I need it to start at 0, 0. So if I'm going to start at 0, I need the first one to be 5 minus 5, which would give me 0. So I need the cosine of t to be negative 1, which means I need to start at pi. And then if I'm continuing in an orderly fashion from smaller to larger, then I want it to end up at 10, 0. So I want it to end up where the cosine of t is positive 1, which would be 2 pi. So I go between pi and 2 pi. Now, if I look at this one, this will give me the upper half, which we can see right here. And again, I've got it going between pi and 2 pi. So you can see right here that this is pi to 2 pi. And I've got the parameterization here. And when I trace it, notice it starts at the origin and goes counterclockwise and stops right there at 10, 0, right? Now, what would I do if I were doing the blue one, the blue curve on the bottom? If I were doing the blue curve on the bottom, I would again want to start at 0, 0 and end at 10, 0, but it looks like this time it's going clockwise. So I would be starting with 5 cosine of t, 5 sine of t. But in order to get the center shifted 5 to the right, I need 5 plus 5 cosine of t, but I need it to start at 0. So let's say that I started in the blue with x equals 5 plus 5 cosine of t, and I've got y equal 5 sine of t. If I start when t is equal to pi, does that work? Does it start me at the origin? Well, again, cosine of pi is negative 1, so that would be 0. Sine of pi is 0, so that would be 0. So it does start at 0, 0. If I continue on to 2 pi, does it stop at 10, 10, 0? Well, the cosine of 2 pi is 1, so I get 5 plus 5, which is 10, and the sine of 2 pi is 0, so I get 10, 0. So this would work to trace the other one between 2 pi. So this is the other parameterization, which would give me half of the circle as well, starting at 0, 0, going to 10 pi, but this one is traveling through quadrant 4. So let's plot this one. Since I didn't plot this one, let's plot it and see how it goes. So I'm going to click on select, and I'm going to add a space curve. And it's this one. You can see it's preloaded. And what I want is, again, 5 plus 5 cosine t. Make sure you use parentheses around the argument to all trig functions and all natural logs for calc plot 3D. The y value is going to be 5 sine of t. And again, make sure you have parentheses or it won't recognize it. Z is going to be 0 because I'm plotting in the plane. And I want to start at pi and go to 2 pi. And now I need to hit enter so it will plot. And I'm going to tell it to graph it in a different color. Notice that I clicked on the gear symbol. First thing I want to do though is click use constant primary color. And then notice how it popped up this blue bar. I can click in the blue bar and it gives me the option to choose a different color. So I'll plot in hot pink. All right, so you can see it right here. Now let's trace it and see if it goes from the origin over to 10, 0. And it does. All right, let's take a look now at parameterization of a line. All right, so we want to parameterize a line in 3D. Now to parameterize a line, we need a point and a direction vector. So let's say that our line is going through the point 432 and has a direction vector ABC. We want to find conditions on the values of A, B, and C so that the line in part A goes through the origin. All right, so first we're going to write the parametric form of a line, which is going to be 4 plus AT equal 3 plus BT equal 2 plus CT, where the constants are the point it goes through. A, B, and C is the direction vector of the line. Now we want to make sure that this line not only goes through 432, but also goes through the origin. Now, there are lots of different possibilities that we can do that will make that happen. Basically, we need it to be a multiple of the direction vector that goes to 432. One of the options for that is simply to use 432 as the option. The relationship between the components of the direction vector need to stay 4 to 3 to 2. That is, A divided by 4 should be equal to B divided by 3, which should be equal to C divided by 2. It's got to be a multiple of the position vector that goes through 432. So I could use 432, or I could multiply 432 by 2, and that would give me 864. That would work. Or I could multiply by some other value, 3, and I could get 12, 9, 6. That would work as well. So all of those are multiples of 432, which will guarantee it goes through that point and the origin, because the standard position vector does go through the origin. So in this case, I believe I just chose 432, and you can see that I went ahead and wrote the vector parameterization of the line here. 4 plus 4t in the I hat direction, plus 3 plus 3t in the j hat direction, plus 2 plus 2t in the k hat direction. These could also be written without the standard unit vectors in the angle brackets, representing a vector valued function. Now let's take a look at what this one looks like over here. And you can see the line right here. The black dot is the point 432, and you can see that it is going through the origin. All right. Let's look at parameterizing a line segment. So not the whole line, but just part of the line between two particular points. So this time I want to plot the line segment through the point 1, 5, and 8, 15. All right. To parameterize a line segment, we restrict the value of the parameter t to go between 0 and 1. To give the whole line, we would just let t be anything. So here are the formulas for vector parameterization of a line segment in 3 dimensions. And what we have, of course, we can just make it into 2D by setting the x and the y. And we just have an x naught, y naught, and an x1, y1. And we want ours to start at 1, 5 and stop at 8, 15. So the start, x naught will be 1 and y naught will be 5. and x1 will be 8, and y1 will be 15. So once we set those in, we can simplify our equations here, and we come up with x equals 1 plus 7t, and y equals 5 plus 10t. So this will parameterize and draw the line in the direction from 1, 5 to 8, 15. Now let's go ahead and take a look at this one in the two-dimensional. And I'll have to scroll down a little bit so we can see it. The yellow is not showing up quite as well, but it's right here. And notice the parameterization is set from 0 to 1. And as we animate, it moves along the line from one point to the other, right? And that's parameterizing that single line segment. Right? Now let's go ahead and take a look at the entire line, which would be the next one. How would I get the entire line between those 2 points? To get the entire line between the 2 points, I simply need to widen out what I allow t to be. In other words, negative 10 to 10 is sort of the standard for Calcplot 3D, but depending on the particular curve, you may find you have to go further than negative 10 to 10. You might even have to go negative 100 to 100 in order to get enough of the graph onto the screen. And so you can see the plot right here, and this is in the XY plane. And again, you can see the 2 points, and it's definitely going through the 2 points, right? You can turn it sideways if you want. You can see that from all directions, you can see the points, right? All right, let's repeat example 8, but this time we're going to choose the parameterization differently. We still want to plot between the 2 points, 1, 5 and 8, 15. But instead of going between 0 and 1 for the parameterization, we want to go from 5 to 6. Now, 5 to 6 is a decent choice because the difference between 5 and 6 is the same as the difference between 0 and 1. If not, I would have to make a further adjustment for it. So 5 to 6 works pretty well too. What does that mean? That means that when t equals 5, I want to be at the point 1, 5. And when t equals 6, I want to be at the point 8, 15. So a different parameterization. And how is that going to work? Well, it turns out that I can simply use the same parameterization I did before, but I need to change it so I can get back to the original. The original is from 0 to 1. So to get t equal 5 back to 0, I subtract 5. So I substitute the parameterization that t minus 5 is the new t, if you will. And then I simply do the arithmetic and algebra to multiply all that out, and I get a different parameterization, negative 34 plus 7t and negative 45 plus 10t. But this time I set the parameter to go between 5 and 6. And when you do that, it's going to plot it exactly the same. So what I've done in the picture below is I left the entire line on there, the whole line, so that you could see the whole thing. And then I did the new parameterization, which only goes from 5 to 6. All right. And you can see that I graphed this one in a darker, thicker blue. So if you're wondering how I got the darker, thicker blue, well, I guess I didn't plot it for you. When you're inside of Calcplot 3D, if you click on the gear symbol right here, one of the options when you scroll down will say curve width, and the default is 2. If you make it 4, it'll be about as wide as it appears right here in this picture. Let's now take a look at how to parameterize the intersection of two surfaces. So we've been talking about space curves, where we're starting with the space curve and we want to parameterize that. But there are going to be many occasions this semester in multivariable calculus where what you have are two surfaces that are intermingling, they're crossing, they're touching, they're intersecting. And we want the curve of that intersection. Right, so before we start, let's go ahead and take a look at the two curves and the intersection. So we have a paraboloid given by z equal 3x squared plus 4y squared, and a cylinder given by y equals 6x squared. So a parabolic cylinder They're both quadratic surfaces. So you can see right here, if I turn it this way, you can see that one of them is a parabolic cylinder right there in sort of green and, well, an orangey rose color, so sort of. And the other one is definitely a paraboloid, all right? So it looks like a parabola from some of the traces. So we have a paraboloid, and it looks like an ellipse from the other. The yellow that you see plotted there is the curve of intersection. So that's the intersection of those two curves. And what we want to do is parameterize that. But we're not given an equation. We're just told here are two surfaces, they cross, they touch each other, go graph that surface. So how do we do that? Well, it may seem obvious after I say it, but it's not obvious for most people to start. When they intersect, when they touch, that means that at those points, their coordinates are equal. So the curve of intersection is basically where the equation of the paraboloid is equal to the equation of the cylinder, but they're not both solved for z equals. So in order to do it, I'm going to make a substitution. Now I'm going to choose x to be the parameter, though this is totally arbitrary. But I did that because I had the cylinder y equal to 6x squared. So it's already in terms of x. So if I choose x as the parameter, then I can write this one in terms of the parameter and do a substitution into the paraboloid and have that also only in terms of x. So I chose the easiest route. So replacing x, or I can leave x as the parameter. So y squared becomes 36x to the fourth, and I substitute that into the paraboloid, and I get the equation z equals 3x squared plus 144x to the fourth. Now this is a fourth degree polynomial which opens upward in the z direction, positive z direction, in the xz plane, crossing the horizontal x-axis at the origin 0, 0. Since we now have both y and z in terms of x, it becomes the parameter t. So we can represent this with t for the x component, 6t squared for the y component, and 3t squared plus 144t to the fourth for the z component. And that will plot that yellow curve, all right? So if we come over here to the plot and we look at it, I'll click in the bar and I can click on the gear symbol. And if I come down here, you'll see right here, I made the curve width 4. So if I made it heavier, it would show up a little better. If I could make it 8 and then hit enter, do you see how it made the yellow darker and wider? So that's one thing that you can do, is to use the gear symbol to set things, right? Okay. We have one last example to work, which is a circle off center in 3 dimensions. So we want to find a vector parameterization that traces a circle in 3 dimensions, but in the plane where y equal 3. So if our origin is here, then y equal 3 would be 1 step, 2 steps, 3 steps to the right, and it would be the plane that would be parallel to the xz plane. The radius is going to be 2 from the center, and the center is the point 33, -4. This last part may throw you at first. It says with a constant speed of 8. What does that mean? It means as you trace it, it has a constant speed of 8. Well, we'll take a look at what that means in just a minute. Let's start with the other requirements. We have a basic parameterization for a circle. X equals r cosine t, y equals r sine t. But we need to shift the center to the given point 33, -4. That means we need to add 3 to the x component. So that would give us 3 plus 2 cosine of t, because the radius is 2. And we need to add 3 to the y component, which would be 3 plus 2 sine of t. well, actually it's in the XZ, parallel to the XZ. So that would be in this one. And then the Y component is 3. So -4 plus 2 sine of t. This is in a plane that's parallel to the XZ plane. So we use X and Z instead of X and Y for our parameterization. Notice that the Y, because it's in the plane where Y equals 3, stays 3. All right. Now, all that's left is to make sure that the speed with which it traces this curve is a constant value of 8. Now, speed is the magnitude of velocity. So it's the absolute value. It strips the direction off of the velocity. Velocity as a vector has direction and length. Speed is just the length. So velocity is the first derivative of the position function, but in this case, r of t is giving us the position on the circle. So if we want a velocity function, then it makes sense that we would do what to it? Yeah, you're right. We're going to take the derivative of it. The derivative of it will give us the velocity vector in terms, or velocity vector valued function in terms of t. So the derivative of 3 plus 2 cosine of t gives me -2 sine of t. The derivative of constant 3 is 0. And the derivative of -4 plus 2 sine of t is 2 cosine of t. Now I need to find the speed. So I take the absolute, I square each term, add them together, and take the radical. That gives me the magnitude, which gives me 4 times sine squared plus cosine squared, which is 1, which gives me 2. Now that is not what I want. I want it 4 times that size. There are different ways of accomplishing this, but the easiest thing to do is instead to go ahead and replace the parameter t in the original representation of position with 4t. If we replace that with 4t, when we take the derivative using the chain rule, we get a 4 coming out front, which will give us 64 underneath. And then the cosine squared plus sine squared is still 1. And we end up with a magnitude of 8. Let's go ahead and take a look at what this one looks like. Here's a picture of what it looks like right here in multi-different colors. Right? So I can close this one down. And I went ahead and plotted the center so you could see it right there. And if I turn it sideways, I can get it right on. You'll see that it is right there where y equals 3. So it is going to be similar to being in the XZ plane, right? I hope this helps you to learn how to parameterize different curves and shapes in 3 dimensions, and that you'll join me for the next video where we're going to be talking about vector valued functions, which we actually used in this video but didn't formally define them. I hope to see you for the next video.